Chemistry doesn't stop at medicines and materials. It also determines the quality of the air you breathe and the water you drink. Every pollutant, toxin, and contaminant is a chemical substance behaving according to chemical rules. Environmental chemistry is the science that explains how human-made chemicals move through air, water, and soil, and why some substances quietly disappear while others persist for decades. This is the Learning Studio, where chemistry is explained as a force that shapes both human health and planetary systems. And after seeing how pharmaceutical chemistry brings medicines safely into the world, the next step is to understand how chemistry also governs what we release into the environment, intentionally or unintentionally. Most people think pollution is just about waste or smoke, but in reality, it is about chemical behavior. For example, when industrial emissions enter the air or chemicals wash into rivers, they don't simply dilute and vanish. They react with sunlight, oxygen, water, and living organisms, sometimes transforming into more toxic forms. Environmental chemistry explains why some pollutants spread globally while others remain local. At the molecular level, environmental chemistry tracks how substances move and change through physical and chemical processes. Gases dissolve into rainwater, solids adsorb onto particles, and chemicals undergo oxidation, reduction, or photochemical reactions. Properties like solubility, volatility, and chemical stability determine whether a pollutant stays in the air, settles into soil, or accumulates in living tissue. This scientific understanding was shaped by researchers such as Rachel Carson, whose work revealed how synthetic chemicals could accumulate through food chains, and Claire Patterson, who demonstrated that industrial lead contamination had spread globally through air and water. Their work showed that pollution is not just visible waste, but a chemical process with long-term consequences. Environmental chemistry also explains water quality. Dissolved ions, organic contaminants, and microorganisms interact chemically with water sources. Treatment methods like filtration, chlorination, and adsorption rely on chemical principles to remove or neutralize harmful substances. Clean water is not just a resource, it is a chemically maintained system. Air chemistry is equally complex. Pollutants released into the atmosphere participate in reactions driven by sunlight, creating smog, ozone, and fine particles that affect climate and health. Understanding these reactions allows scientists to predict air quality, design cleaner fuels, and reduce emissions that harm ecosystems and human lungs alike. Environmental chemistry ultimately transformed how societies regulate chemicals. Instead of reacting to visible damage, scientists could now trace pollutants back to their sources, predict their fate, and assess long-term risk. This shifted environmental protection from guesswork to evidence-based policy. And once we understand how chemistry governs pollution in air and water, the next question naturally follows. If chemical reactions influence the environment at a global scale, then how does chemistry explain large-scale climate processes and atmospheric change? That question takes us directly into the next episode, where we explore climate and atmospheric chemistry, the science behind climate change itself.